Hey everybody, welcome back to another Robison rant, and yeah, let's keep going. So last time we worked an example problem of an RLC circuit that has a step response. We're throwing a switch and then looking at the behavior of the circuit at the time that the switch is thrown, t equals 0, and that helps us figure out how the switch is going to behave in the future. Okay? So it's an arduous, as you saw, it's an arduous process. It would be nice if we could speed it up a little bit. And so I figured, okay, we'll start off with these charts, and hopefully you can see how it kind of speeds things up to a degree, and also how we could have used these past charts to make our lives easier. Now you say, why didn't you give them to me first? It's because you really need to play around with the differential equations and get an idea about how you're supposed to apply these initial conditions, if you will. So I have two of them. I've pulled them for a different resource. And your book has a similar chart. It's just it takes up a couple of pages. So I just thought that these were a little bit more condensed, if you will. So the first one I would pull up is this. And it's using a little bit of different terminology. So let me walk you through this. So it says the natural response of the second order circuit. What it means is that you have no external supplies. So you don't have any of these current supplies or these potential supplies attached to the circuit. What you've done is that you have charged up the capacitors to some value and the inductors to some value. Okay, so those are the supplies in the circuit itself. So that's what it means by this phrase natural response. Okay. And you see the table highlights that you have to determine whether it's over, under, or critically damped. So if you can figure out, if you know over, under, or critically damped, then it's a simple matter of going through and figuring out which thing do you want to apply. So if you have it over damped, you know the solution looks like this. And the thing that I find particularly useful is this over here on the right hand side. So what X represents, that could be the time varying current or the time varying potential, either one. Okay. So, and then over here it says, okay, well, if you're dealing with, let's say, the time varying current, then at X naught, you have some relationship between the two coefficients. And you would have to set this equal to, the initial current flowing through the inductor, for example. And then you'd have to look at the derivative of X naught, the changing current, and then this gives you your coefficient values. Okay, yeah, there we go. So it's just helpful. It's a helpful shortcut for determining the coefficient values and also the equation itself. Let me get rid of that. Of course, you say, well, Greg, that's all fine and dandy if I'm starting off with a charged capacitor and inductor. That's stuff that we did a while ago. What happens if I have these switches where I actually have supplies in my circuit? Okay. So that's what this other chart is for. And again, in the vernacular of this textbook that I've pulled these charts from, what it's referring to as step response is when you throw a switch to connect your capacitors, your inductors to some external supply. Okay. Or indeed, it doesn't necessarily have to be currents or potentials. I guess it could also be, as we have seen, charged capacitors, additional charged capacitors, or other charged inductors somewhere else. And again, we notice that it depends on whether it's overdamped, underdamped, or critically damped to dictate which equation we should be using. And then in addition to that, the necessary initial conditions for us to get the unknown coefficients. Okay. So that's, and we'll take a little bit of practice on these charts. These charts just kind of take care of all of some, or I shouldn't say all of, but some of the calculus that we need to do in order to, arrive at these points. Okay. Cool. Okay. So let's get at it. So I have another circuit for you. Go ahead, take a minute. Let's see if we can find IL of t for when t is greater than 0. You got it? Okay, sweet. Okay. Well, of course, we need to still solve the circuit for the initial states. Okay, those charts don't help us out with that. You still need to know what value you're dealing with prior to the switch being thrown. So we have to deal with that. And let's see here, at time equals 0, this switch closes and that switch opens. So initially what we're dealing with is something like the 80 volts here. We have our 10 ohm resistor. We have a 10 ohm resistor here. So we'll put 10. And this switch is being closed. So right now we have our capacitor. Now that switch is open at time equals 0, so I can draw the bottom line but not the top. And then we have our inductor, our 1K resistor, and our current supply. So we're dealing with some circuit like this. And in fact, you can almost think of it as being two separate circuits, right? There is no current flowing in this part of the circuit. And so it's almost as if these two circuits are not electrically connected at all. Okay, well, that will tell us what the potential drop across the capacitor is, and it will tell us the initial current flowing through our inductor. In fact, the initial current flowing through our inductor must be the 10 amps, right? At a long time, this inductor acts like a wire, and so no current is going to flow through that 10K resistor. It's like it's not even there. Whereas on this other side, we notice that, okay, well, we have 80. At a long time, this capacitor acts like a brake. And so we know that the current running through these these resistors, the current running through those is going to be that 80 volts divided by 20, that 20 ohms. So we have 4 amps sitting over here, which means the potential drop across the capacitor is the potential drop across that 10 ohm resistor. So I can put, excuse me, I've been doing C naught, must be 40 volts. Now, if you prefer to work that in terms of variables, this would just be the initial I. I'll call it I'll just call this I. And of course, this would be something like, I'll say R2 divided by R1 plus R2 times your potential supply. So I'll call this R1, I'll call this R2, call that V. Okay. So if you like to work in terms of variables instead of numbers. Good so far? Okay. So we're done with that piece. Okay. Now when the switches are closed and opened, so let's see what happens. At time equals 0, essentially we disconnect that portion of the circuit, this right-hand portion, and we connect the left-handed portion together. Okay? So let's go ahead and look at that. Okay. So I've gone ahead and taken the liberty of redrawing the circuit and graying out the right-hand side. Excuse me. And so what we're dealing with now finally. Now, in order to use that chart, so the tables that I showed you originally, in order for us to be able to use those, we have to at least get to the differential equation. Okay? And once we're there, then we should be okay. So we have to get to the differential equation and find out which responses we're dealing with. So I'm going to go ahead. Let's use node voltage. And I will go ahead and set the bottom node to ground. And so if we use node voltage, we can write something like the potential at the upper node. I don't know, I guess I'll call it A. So the potential at A, and I'll just start with this left-hand branch. Okay, so we have this 80 over 10. So I'll work in terms of variables here, or numbers. And then I have this plus VA over 10. Okay. Now remember, I have to think about the current going through the capacitor. So I better set this equal to I through the capacitor, right? That's this branch. And then I should think about the current flowing through the inductor. And that whole rigmarole better be equal to 0, right? Well, now we go to our handy-dandy equations. We know that because of my choices, the node potential is also the drop across the capacitor. So I can write that as Q over C. The charge on the capacitor times divided by the capacitance. And taking a time derivative, assuming that I am charging the capacitor plate. So I get something like IC over C. Similarly, for the inductor, the node potential is going to be equal to the inductor value times the current, flowing through the inductor, the changing current. And so again, here I am stuck with 1 over L integral of the node voltage equals, I'll put it as IL. I guess technically it should be IL minus I naught. Since I'm doing an integral, I'm going to do a derivative anyway to get rid of it, so that's fine. We're gonna end up using this top one. Okay. Yes, in fact, let's go ahead and do that. Let's take a time derivative, and I will now employ my dot notation. Okay. And now we see that the changing current through the capacitor is just simply another time derivative. So I'll go ahead and plug that in now. And we have something that says V dot 1 over 5 plus CV double dot plus V over L equals 0. And I've decided to swap. Apparently I'm mixing variables and values. Okay, so I guess I should put, instead of V and C here, I should put the 250 micro, and I should put the 16 millihenries. And we're golden, right? Now we have an expression. Let's see, 1 over 5 times 250 micro V dot plus V divided by 250 micro times 16 milli. So maybe I should have left in terms of variables up until that point. oh well, life goes on. We now have our differential equation, and by looking at comparing these two coefficients, we can figure out what the final solution looks like. So what do we have? And be more specific, what we need to compare is how does that B coefficient right here, call that B, and this C coefficient, we need to compare those two values. So what we're interested in knowing are the values of that B coefficient squared and that value of that C coefficient. Okay. I'm thinking about the quadratic equation. Okay. So let's go ahead and calculate that. Well, B is, okay, we'll put the 1/4 out front. And then we have something like 1/5 squared times 10 to the 6th over 250. And that whole rigmarole is squared. And unless I fat-fingered something, this should end up being something like 16 with 4 zeros, 1.6 times 10 to the 5th. That other coefficient, what I'll call it C right now, that's equal to 1 divided by the 250. So I guess I'll say 10 to the 6th times 250. And then I also have to have 10 to the 3rd divided by 16. Okay. So there's my capacitor value and my inductor value. And again, unless I have done something grossly wrong, you should have something like 250,000. In other words, we have an underdamped situation. And actually, it's always nice when we have an underdamped situation. I'll say omega d is given by the difference between these two values square rooted. So the 250,000 minus the 660,000 square rooted. Yeah, and you should be able to do that in your head, right? This is 9 times 10 to the 4th square rooted. So this is just simply 300. Right? 10 to the 4th divided by 2, that's 100. 9 square rooted is 3, so it's 3 times 100. Well, if we go to our handy dandy chart now, and this is the power of that table, is that now that we know it's an underdamped circuit, we know what the general solution for both the current and the potential look like. So that's why the chart leaves it in the way that it does. Let's go ahead, since we're asked about the current, I'll say we know that the general form of the current now is something like the final behavior of the current. So it has X final. What that means is the final end value of the current. Okay. Then we have plus this B1 prime cosine of, now it's omega d, I'll go ahead and put in the 300 here, plus the B2 prime sine of 300. And again, I've put in the value there. And I'll close that off. And then we have e to the negative. And now this book uses the notation alpha instead of what you can think of as that's the value of b over 2. Okay. So if we take, let's see, we have b over 2 squared is 160,000. So b over 2 is just 400. So there is the solution to the differential equation for the current flowing through the inductor. And what we now have to do is take that general solution and tell it what's the final behavior, what's the end current running through the inductor. And then we have to also figure out what these B1 and B2s are using the rest of the initial conditions. Okay? Well, let's go at that. The handy-dandy table also tells us, for example, that the current at time 0, okay, whatever value that is, should be the final current plus B1. And we, of course, already know what the initial current through the inductor at time equals 0 should be. We found that at the very beginning. This should just be 10. What we have to think about for a moment is what is the current long time at time equals infinity after the switch is thrown. And for that, we can think, oh, wait a minute. We have a potential source, a 10 ohm resistor, and then after that, a 10 ohm resistor, a capacitor, and the inductor. At a long time, the capacitor is going to be charged to some final value. And hopefully you see it. All of the current's going to run through the inductor. Right? This is 80 volts. 80 volts, 10 ohms. And all the rest of the current's going to run through the inductor. That means that this final value, I final, better be 8 amps. So now we're good. We have some idea about how to get B1. It better be 2. Well, let's go ahead and get the other value, right? Not only do we have to worry about that, we're also told that we have to think about DIL dt evaluated at time equals 0. And whatever value that is, that's going to be our negative alpha times B1 plus omega d times B2. Well, we already have the value for alpha. So this would be negative 400. B1 is 2. Omega is 300. We have B2. And what we're left to find is what the initial current, changing current through the inductor is. But we already have that, right? The initial conditions. At the initial condition, we know that the potential drop across the inductor better be equal to the potential drop across the capacitor. So I could write this. And we have values for that. This is 40. We divide by our 16 millihenries, and that must be equal to the change of the inductor's current at time equals 0. Well, what is this? This is 40,000 divided by 16. So this is 10 to the 4th divided by 4. So I believe 10 to the 4th divided by 4. So this would be 2,500. Unless I boggled something there. And we're off to the races. Okay, so we have something like, oh yeah, you can see it. 800 plus 2,500, so I get 3,300. And so I get something like B2 is equal to 11. And we're done. We now officially have our final answer for IL. It's the final behavior as the switch stays closed for a very long time. That would be 8. Then we have added to that B1, which is 2 cosine of 300t plus 11 sine of 300t times e to the negative 400t. Right? And we're done. There we go. Of course, we could have done that differently. For example, let's say if we wanted to use our handy dandy stuff to find the changing capacitor potential, okay, which is perfectly reasonable. We could do that as well. Okay. Well, the final value of the capacitor potential, right, if we're thinking about the final value of the capacitor potential, should be 0, right? This should be 0 because the inductor acts like a wire and the capacitor is in parallel with the inductor. And so the potential drop across the capacitor would be 0. Okay. Then we also have that the capacitor value at time equals 0 is equal to the final capacitor value. Okay, so at time equals infinity, if you will, plus B1 prime, and we already know that that whole thing should be 40, which tells us, if we're thinking about the the potentials, that tells us that B1 is equal to 40. Okay? Good so far? And then we also have to figure out the second equation that we have tells us that we have to think about the time derivative of the capacitor potential at time equals 0. And this will be equal to, again, our negative alpha is 400. B1, well, we saw now that B1 is 40. Plus our 300 B2. And based on our initial conditions, we've got to figure out what we should write down for this, the change in the potential as a function of time. So we have to figure out a value for dVc dt, and then we're done. But we can get that from the initial conditions. Remember what we had. This is 80. This is a 10. This is 10. Our capacitor and our inductor. And at time equals 0, we know that the node had better be at 40 volts and current flowing through our inductor better be 10 amps. So let's just write down node voltage here. You get 40 minus 80 over 10 plus 40 over 10 plus IC plus 10 equals 0. Oh, goody, goody. Look at this. This 40 cancels that 40. Right? So at time equals 0, those two cancel. And I'm left with the idea that the current flowing, let's see, onto the capacitor or away from the capacitor is negative 10 amps. And then I use the idea that the change in potential across my capacitor is equal to the current on the capacitor divided by C. So now I've got it. At time equals 0, I can write negative 10 divided by 250 micro equals negative, well, let's see, 400 times 40 plus 300 B2. And what do I have? Well, let's see. 1 divided by 25, so I can take out that 0. Or this is 10 to the 6th divided by 25. Okay, equals 16 followed by 3 zeros plus 300 B2. So we're off and running to the races. We have something like negative 40,000. Looks like plus 16,000 equals 300 B2. Oh, goody. So this is what, negative 24,000 divided by 300. So we knock off a couple zeros equals B2. And I think I get something like negative 80 equals B2. Cool. Now notice, okay, so due to our handy dandy table, this means that VC is the terminal behavior as time goes out to infinity, 0. Then we have the plus 40 cosine of omega d, and I got negative 80 there, sine of omega d, e to the negative, I think this is 400t. So hopefully you can see the utility of that table. Okay? I was able to apply the same kind of ideas both for the current flowing through the inductor, IL, or the potential across the capacitor. Cool, huh? Okay. Well, I'll get another example video posted, or maybe a couple more, but I think I'll call it quits for right now so that I can get it edited and posted for you as fast as possible. So stay tuned. Thanks for your attention. I'll see you next time.